All right, to continue on, right, we're on page 49. We're going to go and take a look at the theorem 2.6, which it specifically talks about the derivatives of sine and cosine functions. Okay, so when we are taking the derivative of a sine function, right, if I take the derivative of sine of x, that's going to give me cosine of x. Okay, and when I take the derivative of cosine of x, it gives me a negative sine x. We have to make sure that when we are taking the derivative of cosine of x, we get a negative sine x. Okay, so these guys we do have to go ahead and memorize. Memorize it. Right, so let's go and look at example 8. It's fine. It says derivatives involving sine and cosine, right? So for y is equal to 2, sine of x, 2 is the constant, so I'm going to leave it in. So then my sine of x just turns to a cosine of x. So this becomes 2 cosine x, right? For part B, I'm actually going to go and rewrite this where it's 1/2 sine of x. Right, so again, 1/2 of this is a constant. When I'm taking the derivative of sine of x, that gives me cosine x, or I can go and rewrite it as cosine of x over 2. Okay, for C, right, it's really saying x to the first power, so I do have to go and apply the power rule to the x to the first power, right? It becomes 1 times x to the 0th power plus, and then the derivative of cosine of x, which we know is a negative sine of x. And then I could put it all together, right? 1x to the 0th power is just 1 minus the sine of x. Okay, so you will have to go ahead and memorize the derivatives of sine and cosine. All right, and then we gotta go ahead and talk about the rates of change. So you have seen how derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to another. Right, applications involving rates of change occur in a wide variety of fields. Right, in some examples, it could be population growth, production rate, water flow, velocity, and acceleration. Right, if you guys have been in physics, right, you've seen some of this stuff. So a common use for a rate of change is to describe the motion of an object moving in a straight line. The function that gives the position of an object as a function of time is called a position function. If over a period of time, in this case we're talking about delta t, the object changes the position by the amount of, and we get delta s is equal to s times the quantity t plus delta t minus s of t. Okay, and it's talking about the average velocity. So here we go. It's about the change in distance all over the change in time. And this time we're talking about delta x over delta t. And the way that we want to go ahead and express it is I'm going to take s of t2 minus s of t1 all over t2 minus t1. And these t's, 1s and t's 2s, these are just your points. Okay, so in example 9, it says finding average velocity of a falling object. So if a ball is dropped from a height of 100 feet, right, it says height s at time t is given by the position function. Here we go. We have s is equal to negative 16t squared plus 100, where s is measured in feet and t is measured in seconds. We are asked to go and find the average velocity over each of the following intervals. Okay, so here are my T1 and my T2 points. So I'm going to go ahead and label this one as T1, T2. And I'm going to do the same thing for all these guys over here. Okay, you guys might want to go ahead and pop out your calculator. That's fine to use your calculator. I am going to go ahead and use, oh no, where's my Desmos? There you go. I'm going to go ahead and use, come on, what the hey? Okay, there you go. All right, let's go and get started. So I'm going to go ahead and plug these t values in my function. And now that, there you go. Cool. So here I'm going to have s of 2 minus s of 1 all over 2 minus 1. And where this 2 and the 1 goes into is this guy right here. Okay, so I'm going to say negative 16 parentheses. I'm first going to evaluate it at 2. So I get a 36 minus, and now I'm going to go and plug in 1. 84 all over 1. 36 minus 84, we know this to be, what was that, negative 48? And we're talking about feet per second. Okay, and I'm going to go ahead and do the rest for these guys. Right, so I'm going to go ahead and I'm going to do s of 1.5 minus s of 1 all over 1.5 minus 1. So this becomes 1.5. So then we get 64. I already know from my previous one that s of 1 is equal to 84 all over 0.5. 64 minus 84 gives me a negative 40 feet per second. I want you guys to go ahead and try the third one. All right. So it says, suppose that in example 9 you want instantaneous velocity when t is equal to 1. To do this, you need to take the limit as delta t approaches 0. So here we are. We have instantaneous velocity, or v of t is equal to delta t as delta t approaches 0. And then we see, again, the very similar pattern as if we had the delta x's approaching 0, right? We have s in parentheses t plus delta t minus s of t all over delta t. And that gives me s prime of t, or in other words, v of t. Right? When it's talking about the velocity, it's talking about the derivative of position. Okay, so if it doesn't say average velocity, assume instantaneous, which just means the derivative. So the speed of an object is the absolute value of its velocity. So let's go and try example 10. It says, using the derivative to find velocity. It says, at t is equal to 0, a diver jumps from a platform diving board that is 32 feet above water. The position of the water, or the position of the diver, is given by s of t is equal to negative 16 t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. Okay, so I'm going to first start, I'm locating my function of s of t. Let's just go ahead and find s prime of t. Right? I'm going to use my power rule, so this becomes negative 32t and then plus 16. Right? So the first question, it's asking us, when does the diver hit the water? So at the position, right, when is s equal to 0? Right? We're looking for the time. So I'm going to go ahead and take my s of t function. I'm going to equal it to 0. So I get 0 is equal to a negative 16t squared plus 16t plus 32, and I'm going to go ahead and solve for t. So this guy could take out negative 16, we got t squared minus t minus 2, and then I could just go ahead and factor it. What is that? A t minus 2, t plus 1. So then I get t is equal to a positive 2, t is equal to negative 1. So therefore, right, I can't have negative seconds, so we're looking at 2 seconds, right? Cool, let's go ahead and do part B. It's asking, what is the diver's velocity at impact? So we said that v of t is equal to s prime of t. We already found s prime of t, we did that up above. So I know that s prime of t is equal to the negative 32. Oops, negative. Let me go and add that negative in. Negative 32t plus the 16, right? I know this to be s prime of t and also v of t. This is the velocity. So what is the diver's velocity at impact, right? We said at impact, when the diver hits the water, right, we are left at 2 seconds. So I'm going to take this 2 seconds and I'm going to go ahead and plug in for t. So we are going to go and do negative 32 times 2 plus 16, negative 64 plus 16 we should get a negative 48 feet per second. And that is the answer.